In this section, we're going to talk about solar radiation. You might be wondering why, in a class about the oceans, we're going to talk about solar radiation. Well, it turns out that all the energy on the Earth, on the surface of the Earth, comes from our sun. This solar radiation explains why the oceans are blue, drives circulation of both the atmosphere and the ocean, and as you would expect, plays a large role in the biology in the ocean. Solar radiation travels through space, or travels through any medium, in the form of electromagnetic waves. Before we go on and talk about the details of electromagnetic waves, I just want to take a moment to make sure we're all on the same page when it comes to basic definitions of waves. Electromagnetic waves, like ocean waves, which are much more familiar to us, are what are known as a transverse wave. So this is where the oscillation in the wave is perpendicular to the direction of travel of the wave. So if we consider ocean waves, which we're all much more familiar with, the direction of travel is horizontally across the surface of the ocean, whereas the disturbance or the oscillation is in the vertical direction. So if we stick with the ocean waves for the time being, so in that case, this horizontal black line would be equivalent of the surface of the ocean when there were no waves. So I'm going to call that the free surface. So the crest is the highest point that the wave gets, the oscillation gets above the free surface, and the lowest point is the trough. So this will be below the free surface. The wave amplitude is defined as the vertical distance between the crest and the free surface. The wave length is the horizontal distance between two consecutive wave crests. So now if we go back to electromagnetic waves, these are composed of a pair of transverse waves. So one of these waves oscillates in an electric field and the other in a magnetic field. So in this diagram, the electric field is the green shading and the magnetic field is the purple shading. Electromagnetic radiation is generated from any object that has a temperature above absolute zero, which means from any object. When an object has some heat in it, has a temperature, the molecules and atoms within that object vibrate, which is giving it the energy, which gives it the temperature. The higher the temperature, the faster those molecules within the object vibrate. And the faster those molecules vibrate, the faster they vibrate the electromagnetic fields around them, and so the shorter wavelengths that you get for the electromagnetic waves. So here we have this top panel is temperature from lower temperatures on this side to extremely high temperatures on the right-hand side here. The red line in the next panel is the wavelength, the representative of the wavelength. So at the low temperatures, we have very long wavelengths, and at the high temperatures, we have very short wavelengths. The gamma rays and X-rays have a wavelength of around the size of an atom or even smaller. Whereas at the other end, the radio waves and broadcast waves have wavelengths of meters or tens of meters. The higher the temperature, not only the shorter the wavelength, but also the higher energy in the waves. This explains why X-rays and gamma rays are dangerous for us. They're very high energy and they have scales that can interact directly with atoms and nuclei and molecules. So in this plot, we're now doing increasing distance or increasing wavelength rather than the increasing temperature on the previous plot. So now we have the very short wavelengths over here, the cosmic rays and X-rays and gamma rays on the left-hand side, and the long wavelengths, the broadcast waves, the radio waves on the right-hand side of this plot. You'll notice that there's this very small band in the middle here, which is colored like a rainbow. So this is the visible light part of this electromagnetic spectrum. So this is the part of the electromagnetic spectrum we can actually see in. The visible light section runs from around 400 nanometers to 700 nanometers. So a nanometer is 1/billionth of a meter. So that's a 0.9 zeros and a 1 would be 1 nanometer. So in this plot, we still have wavelength along the bottom, along the x-axis, and the left-hand part of here, it's in micrometers, and then we have a break in the x-axis, and from here on, the wavelengths are measured in meters. 0.4 microns, or micrometers, is equivalent to 400 nanometers. Likewise, 0.7 microns is equivalent to 700 nanometers. So this is our visible light band in here. On the vertical axis, we have the amount of energy in different wavelength bands. So you'll notice the highest amount of energy is in the visible light band, which explains why we see invisible light. There is 7% or so of the energy from, in this case, it's the sun. This is the spectrum you get from the sun, is ultraviolet, so smaller wavelengths than visible light. And then the rest of it is higher wavelengths or longer wavelengths than visible light, with the infrared being closest to the visible light. And then a very long tail out to hundreds of meters for the AM radio waves. So speed of light, or any frequency or wavelength within the electromagnetic spectrum, travel at the same speed, so the speed of light, which is constant in a vacuum. So unlike the other waves we'll talk about, water waves, sound waves, light and electromagnetic radiation can travel through a vacuum, doesn't need a medium to oscillate like water waves or sound waves. As I said, it's constant in a vacuum at almost exactly 300 million meters per second, or 186,000 miles per hour. Now, it's constant in a vacuum, but it decreases in speed when it gets into any other medium. So it slows down when it gets into the atmosphere, the air of the atmosphere. It slows down even more when it gets into water. The speed of light in water is 3/4 of that of the speed of light of air, which is slightly slower than the speed of light in a vacuum. We'll see later in the course that all waves behave in that they will refract or bend towards the medium that has slower propagation speed. So in this case, going from air to water, it will slow down. The speed of light will slow down, which means if we think about it in terms of rays, a light ray in air will become more vertical when it goes into water. So this has implications for us. Our brains are wired to think that light always travels in straight lines. So the fact that light bends when it goes into water means that objects in the water aren't where we think they are. So if we consider this fish, the light reaching the observer's eye here comes up from the fish, but then bends at the water surface. So it's actually not a straight line between the observer and the fish. But the observer's brain thinks it's a straight line, so it's going to place the fish here, where this dashed line of light coming from his eye, if it continued straight when it got to the water surface. So he's going to perceive the fish to be here, when in fact, because the light rays bend at the surface, the fish is at a deeper location. You can see the same thing if you stick a spoon in a glass of water. It looks like it's bending once it's in the glass of water.